Bismillahirrahmanirrahim. Dear students, this is Inorganic Material Chemistry CHEM-3115 and the topic is crystalline and amorphous solids. The key concepts which I will discuss, they are crystalline solids, 7 crystal systems and their interconversion, and finally amorphous solids. Let's start from a little introduction about crystalline and amorphous solids. Think of two kinds of materials. One is diamond and the other one is cotton candy. So what do you think about these two materials? What are the differences between these two materials? Are these two materials similar or they are different? Of course they are different in every aspect. Even then, both of them, they are solids. So what are the differences between these two materials? Simply we can say a diamond is a very solid, firm material. It has definite shape, it has definite geometry, it is incompressible, while on the other hand the cotton candy can be compressed. It will not bear any kind of pressure, it does not have any firm geometry or shape. So this is a little difference between these two materials. So simply we can say the materials can be of two kinds. They can be crystalline or they can be amorphous. So what are crystalline solids? These are the most common type of solids. Their characteristics are they are firm, hold a definite and fixed shape, and they are rigid, incompressible. So generally they have a geometric shape and flat faces. The examples of crystalline solids, they include diamond, metals and salts. To understand the crystals or crystalline solids, we must understand their structures. The particles are arranged in crystalline solids in very ordinary fashion. These particles are arranged in repeating pattern of three-dimensional network, and this network is known as crystal lattice, and the smallest unit of crystal lattice is called unit cell. So we can see the crystal structure by using X-ray diffraction, and by using X-ray diffraction we can get clear information about the crystal structure of a material. Crystal structure and crystal chemistry helps us to understand the crystal structures. Dear students, inorganic materials are mostly in solid state, so this is why solid state chemistry is very important to understand crystalline solids. While talking about crystal structure information, this information includes unit cells, dimensions of unit cells, positions or atomic coordinates of atoms inside a unit cell. The crystal chemistry combines this basic structure information and it gives us information about elements, their principal oxidation states, their ionic radii in a crystal system, their coordination requirements and their preferences for ionic, covalent or metallic bonding. In other words, in any of the crystalline material, what kind of bonding is present, either it is ionic, covalent or metallic bonding. What is unit cell? The smallest repeating unit which shows the full symmetry of the crystal structure. In other words, the smallest repeating unit of atoms which shows all of the properties of a material. In this figure, you can see figure 1.1. It is sodium chloride structure. It has been represented in different aspects. Starting from figure A, we can see this is chloride atom and then sodium atom, again chloride, sodium, chloride. So here is a repetition of sodium and chloride ions. In figure B, some lines have been drawn to differentiate between different arrangements. Similarly, in figure C, there are some lines. In figure D, the atoms have been arranged among cubes. And similarly in figure E and F there are some arrangements. But the question is that where is the unit cell? Which arrangement can be used as unit cell? As we have already said, the smallest repeating unit which shows the full symmetry of the crystal structure, it is we can say this is the unit cell. So here is the unit cell of sodium chloride. It is smallest repeating unit and it shows all of the properties of sodium chloride. In this structure we can see this is a cubic structure. All of the lengths are equal. This is one length, this one is the second one, and this one is the third one. A. We represent them, all of them, by A because all of them, they are alike, they are similar. In this cube we can see at the corners there are sodium atoms, and among two sodium atoms, for example this one and this one, in between these sodium atoms this is a chloride ion, and similarly on this side there is chloride. So after each sodium there is chloride, again sodium, again chloride, again sodium. This process continues in 3 dimensions, but this arrangement in which in one cube there are 8 corners and 8 sodium atoms which are located at the corners of this cube. This is the smallest repeating unit, and this is unit cell of sodium chloride.
The crystal structure of sodium chloride is the simplest crystal system. There are total 7 crystal systems: cubic, tetragonal, orthorhombic, hexagonal, trigonal, monoclinic, and triclinic. These 7 crystal systems can be described on the basis of their unit cell shapes. The cubic system contains all of the lengths equal, all of the angles are also equal, and they are equal to 90 degree. In tetragonal crystal system, one length is different. In orthorhombic crystal system, all of the lengths are unequal, but all of the angles are equal and they are also equal to 90 degree. In hexagonal, one length is unequal and also one angle is not equal to 90. In trigonal crystal system, all of the lengths are equal, all of the angles are equal, but none of them is equal to 90 degree. In monoclinic structure, all of the lengths are unequal. The two angles alpha and gamma, that is equal to 90, and the beta is not equal to 90. In triclinic crystal system, all of the lengths are unequal and all of the angles are also unequal. Students, in this table 1.1 you can also see allowed lattices which are written in front of each crystal system. For example, for cubic crystal system it is PF and I, for tetragonal it is PI, for orthorhombic PFI A, and here you can see in parenthesis BSC. So what is PFI A, B or C? These are actually P for primitive, I for body centered, F for face centered, and C for side centered. We will discuss these terms and these systems in detail. Here is the unit cell of cubic system, then tetragonal, orthorhombic, monoclinic, triclinic, trigonal, and hexagonal. You can see in cubic all of the lengths are equal, so all of the lengths are represented by A. In tetragonal, two lengths are equal, they are represented by A, and the third one is represented by C. In orthorhombic, all of the lengths are unequal. In monoclinic, all of the lengths are unequal and one angle is also different. In triclinic, all of the lengths are unequal and all of the angles are unequal. In trigonal, one angle is unequal, and in hexagonal one angle is of 120 degree. These are 7 crystal systems. Now we will talk about conversion of these 7 crystal systems into one another. These 7 crystal systems can be converted into each other, starting from cubic symmetry. It can be converted to tetragonal and tetragonal to orthorhombic. So here is the table 1.1. For cubic, all of the lengths are equal and all of the angles are also equal, and they are also equal to 90 degree. So if we have a cubic system, if we stretch or compress the cubic system along one axis, it is converted to tetragonal. By compressing or stretching cubic system along one axis, its one length changes, and A is equal to B, and that is not equal to C, it becomes tetragonal. And similarly, if we stretch or compress a tetragonal system along the second side, it is converted to orthorhombic. And in orthorhombic, we know that all of the lengths are unequal. Similarly, if we share one face relative to opposite face, the orthorhombic system is converted to monoclinic. In monoclinic system, we know that all of the lengths are unequal. Two angles are equal to 90 and the third angle is not equal to 90 degree. So when we share one face relative to opposite face of orthorhombic where all of the lengths are not equal, it is converted to monoclinic. So from monoclinic to triclinic, if we share a second face relative to opposite face, monoclinic is converted to triclinic. Similarly, we can convert cubic into trigonal. So in trigonal, all of the lengths are equal, all of the angles are equal, but none of them is equal to 90 degree. So if we have a cubic system, we stretch or compress along one body diagonal. I will explain it. What is one body diagonal? Then the cubic system is converted into trigonal system. Simply, we can summarize the results of this interconversion. The 7 crystal systems are listed in 1.1, table 1.1, and they are shown in figure 1.3. 6 results we can get from interconversion of crystal systems. 6 of these unit cell shapes are closely interrelated and are either cubic or can be driven from a cubic system by distorting a cubic system in various ways. Thus, if one axis C is different length to the others, the shape is tetragonal. If all three axes are different, the shape is orthorhombic. If one angle is not 90, the shape is monoclinic. Whereas if all three angles differ from 90 degree, the shape is triclinic. And similarly, if cubic system is stretched or compressed along this is one body diagonal, this side and this side. If we compress the cubic from this side and this side, it is converted to trigonal system. Here are 7 crystal systems with their bravest lattices, the words P, C, I, F, and so on. You can see again for triclinic it is only of P type, monoclinic P and C, orthorhombic P and CIF, and similarly tetragonal is PI, and for cubic PIF, hexagonal is P and trigonal is R. So these are 14 bravest lattices which we have discussed earlier in table 1.1. Again we will describe them in detail. So starting from F, what is F? F means face-centered lattice. F contains additional lattice points in the center of each face. You can see this figure. This is one face. This is the second face. This is third face. Similarly, the lower one is fourth. And the front one, this is fifth. And the last face is on the back side. If this lattice contains additional lattice points in the center of each face, these are additional points in the center of each face. You can see this is the lattice point at the center of lower face. This is additional lattice point at the center of upper face. This is right, front and back. This is an example of face-centered cubic system. We also say that this is FCC structure, and this is an example of copper metal. A side-centered A, B or C lattice contains extra lattice points on only one pair of opposite faces. So look at this picture. There are two lattice points at only one pair of opposite sides. These are highlighted by circles. It is labeled as C-centered if the extra lattice points are on the AB face of the unit cell. This is the AB face. This is length A and this is length B, and all of this face is A B face. If the two lattice points are present on one pair of opposite faces, which are AB faces, then it is labeled as C-centered. Similarly, it is labeled as A-centered if the lattice points are present on BC face. It is labeled as B-centered if the lattice points are present on AC face. A body-centered lattice that is represented by I has an extra lattice point at the center of the body. You can see in this figure. This is alpha iron. It is body-centered cubic. So it is represented by BCC because it has a cubic unit cell with iron at the corner and body center positions. It is also important to note that for a lattice to be body-centered, the atom or group of atoms located at or near the corner must be identical with those at or near the body center. Here is an example of sodium chloride. It is cubic system. We can see there are sodium atoms at the corner, but this structure is primitive. Primitive is represented by P. It is the most common Bravus lattice. This sodium chloride is primitive. It is not body centered. Even there is a chlorine atom at the center of the cube, but this chlorine is different from the atoms, sodium atoms, which are present on the corners of the cube. So this is why this structure is primitive. The combination of crystal system and lattice types gives the bravest lattices of the structures. There are 14 bravest lattices which we have just discussed. Again, I can show you the 14 bravest lattices. One is for triclinic, two for monoclinic, then four are for orthorhombic, two for tetragonal, cubic contains three bravest lattices and hexagonal one, trigonal one. So there are 14 bravest lattices. Dear students, crystal structures may be described in various ways. The most common and one which gives all the necessary information is to refer the structure to the unit cell. The structure is given by the size and shape of the cell and the position of the atoms, in other words, atomic coordinates inside the cell. However, a knowledge of the unit cell and atomic coordinates alone is often insufficient to give a revealing picture of what the structure looks like in three dimensions. The latter is obtained only by considering a larger part of the structure comprising perhaps several unit cells and by considering the arrangement of atoms relative to each other, their coordination number, interatomic distances, types of bondings, etc. It then becomes possible to find alternative ways of visualizing structures and also compare and contrast different types of structures. There are two most useful ways to describing the structures. There are two most useful ways of describing structures which are based on close packing and space filling polyhedra. The close packed structures, we will discuss about close packed structures which are cubic and hexagonal close packing. We know that many metallic, ionic, covalent and molecular structures can be described using the concept of close packing. The guiding factor is that the structures are usually arranged to have the maximum density. Maximum density means the atoms are ions, they are closely packed and there are no so much free spaces among them. The principle involved can be understood by considering the most efficient way of packing equal size spheres in three dimensions. Look at this picture. These are spheres of equal size. They can be closely packed. If we consider the sphere A, this sphere is surrounded by 6 spheres. So its coordination number, we can say the coordination number of A is 6. These 6 spheres, they are along 3 axes. These number 3 and 6, they are along x axis. 2 and 5, they are along y axis, and 1 and 4, they are along z axis. So if we repeat this unit, we use more cubes here, we can get more complex structure. The coordination number of 6 is the maximum possible for a planar arrangement of contacting equal sized spheres. Lower coordination number is also possible. For example, look at the picture B. The atom A is surrounded by 1, 2, 3, 4 spheres. There are some empty spaces. So these spheres are not closely packed. This is why the coordination number of A is 4. Less spheres are present around the sphere A. It is also important to note that within a close packed layer, three close packed directions occur. I just mentioned before, x-axis, y-axis, and again we can see this figure. This is close packing along x-axis, this is y-axis, and this is z-axis. Now I will talk about if we place a second layer on the first layer, what will happen. The most efficient way for two close packed layers A and B to be in contact is for each sphere of one layer to rest in a hollow position between three spheres in the other layer. Just look at this picture C. We have atom A, it is surrounded by different spheres. The hollow positions are of two types. One are in this row and the others are in upper row. So these hollow positions, they are represented by P, and these hollow positions, they are represented by R. Atoms in the second layer may occupy either the P position or they may occupy the R position. If atoms in the second layer occupy P position, then they cannot occupy the R position. And similarly, if the atoms in the second layer occupy R position, they cannot occupy the P position. The most efficient way to pack spheres in 3 dimensions is to stack close packed layers on top of each other. There are two simple ways to do this, resulting in hexagonal close packing and cubic close packing. It is explained in detail here. This is A layer, which is represented by blue circles, and we just mentioned in previous slide that there are two positions where the atoms of the second layer can reside, P position and R position. The most efficient way to pack spheres in 3 dimensions is to stack close packed layers on the top of each other. There are two simple ways to do this, resulting in hexagonal close packing and cubic close packing. Just look at the figure. The B layer is represented by the circles of pink color, and if we see these circles, there are two kind of spaces. One is represented by S and the other one is represented by T. So the second layer, which is represented by A, here the circles are blue in color. The second layer has two possibilities. The atoms of the second layer can be resided on empty space T, or it can be resided on empty space S. As mentioned here, the atoms of the A layer, they are resided on the empty space S. Now after residing the atoms of A layer, there are again two possibilities. The atoms of if we want to place the third layer, the atoms of the third layer, they can occupy two positions. One position is this one, I am just mentioning by the cursor, and the second position is this one. So if the atoms of the third layer, they are placed on this position, the third layer atoms will occupy the same position which is occupied by the first layer, B layer. And if we place the third layer at this position, then the third layer atoms will occupy a new position. So I will explain it further on next slide. You can see this figure. Thus the basic, if starting from B layer, this is represented by pink circles, and after B layer there is A layer, which is represented by blue circles. And now look at the C layer. The C layer atoms, they are placed on a position which is not A position, neither B position. So this is the two possibilities. The third layer can be placed exactly on the second layer or exactly on a new position. So if the third layer is placed on a new position, we get A, B, C pattern. And after that, the fourth layer will occupy the same position which is occupied by A atom. So this process will continue and we will get ABC pattern. On the other hand, if we place the third layer on the same position which is occupied by the first layer, then we will get AB pattern. So this pattern is called cubic close packing. The space between the atoms in crystalline structures are very less due to high intermolecular forces. This results in crystals having high melting and boiling points. The intermolecular force is also uniform throughout the structure. Crystals have long range order. This is the difference between the crystalline and amorphous solids, that crystalline materials, they have long range order. It means the unit cell is being repeated over a great distance. The inorganic materials are mostly in solid state. This is why we discussed all of the crystalline systems, and you have learned about 7 crystal systems. There are 14 Bravas lattices and close packed structures. Now let's talk about amorphous solids. Amorphous solids are rigid structures, but they lack a well-defined shape. They do not have a geometric shape, so they are non-crystalline. This is why they do not have edges like crystals have. In non-crystalline solid, the atoms and molecules are not organized in a definite lattice pattern. The most common example of an amorphous solid is glass. Other examples include plastics, various polymers, waxes, and thin films. Solids and liquids are both forms of condensed matter. Both are composed of atoms in close proximity to each other, but their properties are of course enormously different. While a solid material has both a well-defined volume and a well-defined shape, a liquid has a well-defined volume but a shape that depends on the shape of the container. So liquids are an example of amorphous solids where the atoms does not have definite positions. Similarly, a solid exhibits resistance to shear stress while a liquid does not. Externally applied forces can twist or bend or distort a solid's shape. Solids exhibit resistance to shear stress while liquids does not. In other words, we can say if we compress a solid, the solid particles will bear the stress and they can retain their original shape. On the other hand, liquids flows liquid flows under the action of an external force. It does not hold its shape. These macroscopic characteristics constitute the essential distinctions that a liquid flows lacks a definite shape and cannot withstand a shear stress. A solid does not flow, has a definite shape, and exhibits elastic stiffness against shear or stress. Here is a picture. We can see these are atoms and molecules in a liquid, and these are atoms and molecules in a solid. We can see the atoms or molecules, they are orderly arranged in a solid, but they don't have any order in liquid structure. In short, we can say the solids have atoms which are present at definite positions, but liquid does not have atoms. This variation in characteristics of solids occurs due to the arrangement of their molecules. Here the particles of matter do not form a three-dimensional lattice structure that we have seen in solids. Some naturally occurring have, just like liquids, there are many solids which do not have ordered arrangement of atoms or particles among their structure. So these kind of solids, they are called amorphous solids. Amorphous solids break into uneven pieces with irregular edges, and they do not have any distinct arrangement or shape of molecules, so they cannot be identified by their structure as crystals. These are the differences between crystalline and amorphous solids. Crystals have an orderly arrangement of their constituent particles. In comparison, amorphous solids have no such arrangement. Their particles are randomly organized. Crystals have a specific geometry shape with definite edges. Amorphous solids have no specific geometry in their shapes. Crystalline solids have a sharp melting point on which they will definitely melt. Amorphous solids will have a range of temperature over which it will melt, but no definite temperature as such. Crystals have a long order arrangement of their particles. This means the particles will show the same arrangement indefinitely. Amorphous solids have a short order arrangement. Their particles show a lot of variety in their arrangement. Crystal solids break along particular points and directions. Amorphous solids break into uneven parts with ragged edges. Crystals are also known as true solids, whereas another name for amorphous solids is supercooled liquids. In this picture, we can see on the left side the figure A. This is a crystal structure. The B is an example of glass, which is amorphous solid, and C, for comparison, it is a gas where the molecules are not interconnected, because in gas we know that the intermolecular forces are very weak. At the figure A, the atoms are arranged in a specific pattern, and we can see this arrangement on long order scale. So this is why we say the crystalline solids are long range order crystalline solids. On the other hand, if we look at the glass, the atoms are interconnected with each other, but they don't have specific regular pattern. Just like here, this is one sphere of a specific size. This one is of small size, again larger, more larger and larger. So in amorphous solids, the atoms are not arranged in a specific order. So this is difference between crystalline and amorphous solids. The references for this lecture, there is one book, Solid State Chemistry and Its Applications, by Anthony R. West. These are some websites the students can use these links to get more knowledge. And for assignments, students have to practice to convert crystal systems into each other. Students have to search and summarize different inorganic solids and their structural properties. I will try to add these references for this lecture, which are one book and two online links. I will try to add one book and two online links, and I will try to add the soft copy of this book on Google Classroom. Thank you so much. This is all about the lecture.